on the day that you skip the first one.
All right.
You unavoidably miss.
I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for the students. Just ask you to bless this class today, Lord. In your name I pray. Amen. All right. So now we've got all of the globally mostly locally politically incorrect comments today. Any of you have Ganakan? Is that how you say his name?
I did.
Have you talked to you about locality?
Yeah. Wait, that was a church one yesterday.
Yeah.
Oh, I just had it for class.
Yeah. I wondered if he talked about locality in class too.
He might have.
Like the global local,
Yeah.
global and local.
He might have.
Glo- I was hoping yesterday he would say, like I love it when he says, we need to stop seeking power. How does he say it? We need to give up on the love of power and instead, he flips it around. Instead of, curses. He has so many phrases he turns around that are very memorable, except I can't remember them, so I guess it didn't work. Oh well. I listened to both services, though. He has most of the same content, but the second service is a slight improvement.
But how's the first one?
Yeah, because he said it was controversial to say that you are the church wherever you go, and then the second time he just said that you are the church wherever you go. Because I think he decided that it wasn't that controversial, which I think is reasonable, because I think the church is people, not buildings. But heritage? Yeah. Okay, anyway, any questions?
How about number 9?
Number 9?
I'll say that was fun. You're not. That's fun. No fun.
Prove that is an algebraic extension of Q. However, if it's not a finite extension. So certainly not finite because it has the nth root, right? The nth root of 2 in it. And for arbitrary n, which means that, that's not finite, right? I mean, there's infinitely many elements in there which are not in Q, which means, and there's...
Do you just say that?
I guess if you want to be fussy, you need to show that those are independent extensions. Well, what's the worst thing that could happen is somehow that infinity of extensions somehow collapses back down to a finite extension, but I think you don't have to worry about that because you can show that x to the n minus 2 is irreducible for arbitrary n. Therefore, that's not finite. I mean, let's look at it and see if I actually have contributed. Now, some of these solutions, as you well know, Kristen, are not complete, right? Like there's some things in here missing. Oh, that's foreboding. I suspect the solution above can be improved. Never comforting words for me to read. Let's see here. Let's see here. So I start. Well, first of all, it's algebraic, right? Because every element in it is the 0 of that polynomial, right? Not that polynomial, but there exists a polynomial which it's the 0 of. So it's algebraic. And the Q adjoining the nth root of 2 is a subfield of degree n, and n is unbounded. I think that's really a complete solution. I have the same sort of misgivings as you do when I was writing the solution, but I think it's actually complete. Yeah. If you can find a way to improve it, I would be interested. Yeah. Other ones we can talk about? I mean, certainly a proper solution should contain the statement x to the n minus 2 is irreducible by Eisenstein with p equals to 2, right? But that's nth order irreducible, which means that it's a degree n extension over Q, but n is arbitrary, right? So that's very much not finite dimensional, right? And that's just part of what's in here, right? Because we're like adjoining the square root of 2, the cube root of 2, and so forth and so on. I mean, I don't know, I guess if you think of it, that's kind of an interesting question if you cap this off, right? If you say q adjoin root 2, cube root, fourth root, fifth root, sixth root, seventh root, eighth root, ninth root, 10th root, all the way out to the 10th root of 2, right? Like, what's the degree of that extension over q? Because the things you're extending by in that conversation, they're not independent, all of them. Some of them are, right? Like if you adjoin the square root of 2 and the third root of 2, that's the same as adjoining the what? The sixth root, right? So if you think about going from the square root to the 10th root, sorting through it, maybe you could figure out what would it be like. What's a minimal set of generators for that thing? I mean, I can get, for example, I can get the second and the third by adjoining the sixth, right? The fourth, how can I get the fourth? If I get the fourth, that gets me the square. If I get the eighth, I guess I get what? The 4 and the 2. So it seems like if I adjoin the 8th and the 9th root, that'll get a lot of everything, except it won't get what? Won't get the 7, the 5.
But 10 would be
Yeah, 10 would be begotten. Hey, it's a new use of begotten. Also incorrect use, but yeah. What? 7. Yeah, it seems like we need 5. I think we need the 5 and the 7. I think we need 5, 7, 8, and 9. I think with those we can get everything.
You get 10 with 5?
With the 8 and with the 8 and the 5, because we do the 8th root to the what, 4th power, that gives us square root of 2. I think with the 8th root we can generate the square root. I mean, like, so it seems like the algorithm is something like you pick the highest prime power that appears before where you're cutting off, and make sure you got a copy of each prime as large as it appears. Something like that. I don't know, just talking. But any other questions? I thought Captain Marvel was pretty good. Not as good as the Thor movie. Better than Captain America, I'd say, but I don't like Captain America, so what can I tell you? Haven't seen it yet? Oh, Batman dies. Sorry.
Oh, darn. You guys told me that.
It's like some of my brothers spoiling The Last Jedi. He's like, yeah, Batman dies, and thanks, Bill. Very nice. Other questions? You guys have other questions?
Could you show us the list of questions again?
Sure.
Oh, wait. I have them right here. I did.
I think there's a theorem. I'm trying to remember if it's over a general field. I mean, so if we join the square root of 2 and the square root of 3, we can look at that instead as adjoining the the square root of 2 and the cube root of 2. We can look at that instead as adjoining the sixth root of 2. So like, generally speaking, is it possible, say, f adjoin alpha and beta, to look at that as, say, f adjoin a single thing gamma? Is there can we always recast a given extension by two things as an extension by one thing? When is it, or is it not possible? You say not?
Well, like the square root of 2 and the square root of 3. I don't think that.
Wouldn't it be the square root of 6?
I thought we did an example where it was.
There's a theorem. I think, though, if we do q adjoin root 2 and root 3, you say? that that's Q adjoin root 6. And let's see here. To get the square root of 2 from root 6, how would you do? If we square it, right? Oh. Huh. Am I wrong? Maybe I'm wrong. Show this is not true? Why am I thinking this is true? Well, I am remembering from a simpler time that I had these notes, and one of the things I remember as I was studying Galilean is he has this really snazzy theorem. If I can find this stupid thing. I think it was Stein. I could be wrong, though. Ah! Stupid fast scrolling got me again. There it is. There it is. Primitive element theorem. Stein, how do you say it? Steinitz? 1910. If you have a characteristic zero field in algebraic A and B, then there exists a C such that F adjoin AB is just F adjoin C. The proof is given on page 367 of Galilean. It doesn't, I'm not saying it's necessarily root 6 here. I'm not sure at the moment, but.
But if you had like the square root 2 and pi.
Ah, that is true. The square root 2 and pi would be, yeah, no. So that's a kind of fun question, right? I mean, given a couple of elements, can you find the primitive element that recasts it as an extension by just one thing, you know? I mean, there's a, maybe this is an attack that you could use. I'm not sure, guys, but seems like this is an attack you could use. Something like x minus 2 gets you the root 2, right? And something like x squared minus 3 gets you the other one. So it seems like, you know, if I can find, see, well, does that, yeah. That may be the wrong way to approach. I don't know. I shouldn't speculate because I haven't thought about it too deeply lately. It's an interesting question, though. How do you come up with that primitive element? I mean, certainly you can just write out the. I mean, here's one approach. I mean, this I can tell you, it doesn't take a lot of effort. What is this? I mean, the way to understand that, of course, is Q adjoin root 2 adjoin root 3, right? So if you say that, you know, suppose you got A and B in here, then something in this, if I have something in here, then that means x is equal to something like A plus B root 3, right? Because we know that 1 and 3 certainly span that extension, and they may even be a basis. Knowing that they're a basis is knowing that root 3 is not in Q adjoin root 2, right? Which we've proved before, but that just involves supposing it is, and then if you look at the equations which make root 3 inside the Q adjoin root 2, the equations don't make sense, right? They don't have rational solutions. So then what is this? Well, a and b are in here, right? So that means that there's like a1 plus a2 square root of 2 plus b1 plus b2 square root of 2 square root of 3, right? And so that gives us something like a1 plus a2 root 2 plus b1 root 3 plus b2, well, square root of 6. And I guess it may or may not be obvious. Maybe it's not obvious at all, actually, how to find, because I mean, we're trying to, I'm posing the question, how do you find alpha such that you can express x as like, you know, c1 plus c2 alpha plus c3 alpha squared plus c4 alpha cubed? I mean, like, for an arbitrary thing in this extension by root 2 and root 3, yeah? Here's a jump. Maybe it's just the sum of them.
Yeah, that's true.
That's true.
We proved that.
Oh, you know.
That was going to be my next question about what I wanted you to go over in this class.
Well,
Was problem 21.
huh. It's mildly disturbing. Have you read my thoughts or have I read yours? I don't know.
That's what I said at the beginning, so you're talking about problem 21.
Oh, a coincidence? No, there's no coincidences. I'm going to try to build a flurfin into my Calc 2 test tomorrow.
A what?
A flurfin?
Which is?
That's okay. Let's see here. No one. Don't Google it.
Too late.
Dang it.
Oh, this is not the right thing.
Curse it.
This is paint. I don't know spell it.
All right. Yeah. Well. Oh, so problem 21 is. Oh, well, you know. Well, yeah. There you go.
Well, we should have known that wasn't root 6. We all get this problem.
Correct.
I mean, I should have known it's not root 6 because I assigned this problem, but things leave my mind, as you are well aware. But this is, I mean, if we take that, obviously you got your root 2 and your root 3. Well, is that obvious? I don't know if it's obvious. If you square that, what happens? You get what? Oh, a mess? How did you guys work that problem? Hey, let's look. Go ahead. You got like, no, your answer how it worked the problem is no thanks. I'm not sure that that's a method. Let's see what I did or didn't do.
So one direction was easy.
One direction was easy? Prefer not to think about one direction. Okay, so obviously that is in there. So that's the one direction you're talking about? That inclusion? To see the other inclusion, we need some calculation. So I show that the reciprocal of 1 over root a plus root b is actually equal to that, which then implies the numerators in there because you can multiply by the denominator and still are inside the field that you're working. And we know that Q adjoin square root of a plus b is a field, so it has to be closed under. I mean, Q adjoin square root of a plus square root of b is the smallest field which contains the rationals and square root of a plus square root of b, right? So this, whatever this is, has to be inside that, right? I mean, it makes sense what I'm doing here. And I mean, once you know that this is in there, you can just add and subtract with square root of a plus the square root of b to get square root of a is in there and to get square root of b is in there. which shows you the other inclusion. But is this the only solution to this problem? Certainly not, right? Like it's got to be other algebraic. I'm certain there are other algebraic things you could do to the square root of a plus the square root of b, manipulations with it that are inside the field to generate the square root of a and the square root of b in such a way that you could do algebra with what's given to just isolate. I mean, you got to do something within the operations of the field to isolate root a and root b, starting with the square root of a plus b, which is given, square root of a plus the square root of b, which is given. Does that make sense? Did you guys use the trick that I showed, that I just had up here, or did you find a different path?
Something similar but more complicated.
Okay. You can tell from this large whiteout space that I did something horribly wrong here and had to erase. Other questions? How many questions on the test? Like 3?
On the test.
Like 3?
Well, the first one be like, what is the derivative? Please sign here if you have attended class.
If you have a 90% percentage above 70, sign here and get a whole.
Oh, and then maybe like, if you have above a 42%.
If you have above a 0%.
Second question. Are you here for the test?
Third question.
Correct
What is
answer
the
being
derivative
yes.
of x squared?
I thought you were asking if I was going to be here for the test.
No.
So problem 3, you guys are all good on problem 3 now?
Let's look. Yeah, let's look.
So I think problem, yeah.
I would appreciate the discussion of it being a spanning set. Oh, good.
Oh, great.
That's what I wanted to see.
I love looking at that.
So
I see something similar to what
if you pick x, if you pick x and f adjoin pi, it's essentially a power series. Well, it's not really a power series, honest to goodness. It's a polynomial in pi. Well, no. It's, well, I guess technically that is a polynomial because only finitely many of the b sub m's are non-zero, right? But I don't know. It's just more convenient to let it go to infinity for the sake of not keeping track of the largest one, because where the largest one is isn't really that interesting. It is where it is. But you can take this sum and break it into, well, first of all, the b's are where they're in f, and f is what? Q adjoin pi cubed, right? So the b sub m is some cmj pi to the power 3 to the j, which we can write as pi to the 3j. These are rational coefficients. And then laws of exponents, and then if you just think about it, there's different cases here. M could either be in 3z, it could either be in like 3n, or 3n plus 1, or 3n plus 2, and those 3 different cases give you these 3 different sums, which then can be rearranged like so to show you that 1 pi and pi squared with q adjoin pi cubed coefficients gives you an arbitrary element, which is to say that spanning, as you were asking. Yeah. So that shows that 1 pi and pi squared form a base. Well, they span at least the f adjoin pi. Linear independence, yeah. Linear independence. It may be the same, almost the same stupid calculation. If we,
I think linear independence, we did a different way, and it made sense. We basically arrived at a contradiction.
yeah, if
If like, basically just set C1 plus C2 pi plus C3 pi squared equal to 0, and then just showed that they have to be 0.
right, if we set this equal to 0, right, and we just do this calculation in reverse. Well, if we just do this calculation in detail, we have that the rational coefficients all have to be 0 because of the linear independence of powers of pi. These powers of pi are disjoint. 3n plus 2, 3n plus 1, 3n, these partition the integers, so these powers are distinct. which means by the linear independence of powers of pi, which is to say that pi is transcendental, right? Because if there was some non-trivial combination here, then that would imply that pi is algebraic, which we are happy to accept is not true. They do not pay me enough to prove that in here. That's a hard one. But yeah, essentially your contradiction is the same ball of wax, right? I like problem 4. Did you guys like problem 4? Problem 4 is kind of fun. I don't think, I personally am certainly guilty of not exploiting this technique as much as I should. The idea of probing irreducibility by shifting variables is a very powerful technique, which I don't use enough. I mean, what this is saying is that if f of x is a polynomial and a is an f, then the splitting field for x, f of x, and f of x plus a is the same. Like that's really neat. I mean, that says if, you know, here's an application of this. The splitting field for x squared plus 1, right? And the splitting field for x plus 332 squared plus 1 is the same. Of course we know that's true because the splitting field for both of those is the complex numbers, right? But over a more interesting field, that could be a non-trivial connection there. But the proof was simple enough, right? I mean, I just looked at f of x plus a, assumed that f of x splits in E, right? And then I looked at x plus a and just rearrange it, right? I mean, x minus this, x minus that. So apparently x plus a splits with roots r1 minus a, r2 minus a, rn minus a. What is it? Uh-oh.
It feels to me like you're assuming the point.
Well, we know that there's a splitting field, right? And so the splitting field gives me the existence of a polynomial. It gives me a factorization of f of x. So I'm taking that factorization of f of x, which we're assuming exists, because we're not debating the existence of splitting fields in this problem. That has been elsewhere proved. And I'm just evaluating that at, this really, at x equal to x plus a. So replacing x with x plus a. You know, to make it feel less circular, maybe I should look at f of u plus a or something. I don't know, but we use x plus a. We use x here, but I don't know. I will warn you, I think some of my solutions, I forget to check the minimality of the splitting field. Right? It's not just that it has a 0, it's that it's the smallest field which you have a 0. It's the smallest field for which the polynomial factors into a product of linear factors, right? So you could always throw in more stuff past that and not have a splitting field, right? Like I could take something stupid, right? Like x squared minus 3, and I could say, look, it's got zeros in the complex numbers. Well, that's great, but I don't need complex numbers to split x squared minus 3, right? It splits just fine in the reals. In fact, the reals isn't even the splitting field if we start in the rationals. What's the splitting field of x squared minus 3 as a rational polynomial? Yeah, q adjoin root 3 is the splitting field. So it's the smallest field. Yeah. Problem 5 was very mysterious until you understood how the game was played, right? Once you understand how the game is played, it's not that bad, but also the answer is far from unique. Like the answer could look different. I got to be really careful if I assign this kind of thing on the test to like be logical in my grading. There's more than one way to present the answer because of the Z5. See if here. Problem 6. I love problem 6. The idea of problem 6 is so beautiful. in the sense that I love this. I love problems that when you read the statement, it just seems impossible. But then when you realize the tools that you have at your disposal, it's like, oh, I'm done, right? You differentiate the stupid thing, and it has a repeated root, 7-repeated root of 0, you know? And yet, the original one doesn't take 0 as a 0, so they have no common roots. Therefore, what? It has no multiple 0. Simple as that. So it's important that you understand the role that differentiation plays in the study of multiple roots, right? Let's see here. The other one I would warn you about is, this came up in a previous year when I signed this. I think I put it on a test also at some point. There's one about the nth roots. 25. We'll end with that. Make sure you understand 24. Like, that's a good test problem. There's a lot of ways to ask that in a slightly different fashion. Problem 25 is also important because, like, when I first solved the problem, I got sucked into thinking that I could take A and factor it into a product of alpha 1 through alpha n, where alpha 1 through alpha n are the principal nth roots of unity that are found inside the complex number system. However, understand the context of this problem forbids such. Because you are not given that this field F or this field E have anything directly to do with the reals or the complexes. These are just abstract fields. So we have to work more abstractly here, right? So basically, the point here was that the how did I argue? Well, anyway, I know we're out of time, but there's a workaround here. I don't have the words at the moment. So oh, that's right. I worked out that the quotient of the roots to the first root are all roots of x to the n minus 1 as a polynomial in f of x, which again may not be the reals. I mean, I don't know where this is. This field f is abstract, right? But that only has zeros of 0, whereas the original polynomial has a 0 of, when you plug in 0, you get what? You get minus a, right? So there's no common roots, and that is what I needed to prove that those were distinct roots of unity in E. But I'm butchering the statement of the problem right now. I'm sorry. My point is you might have tricked yourself into thinking you had a complete solution here because you're assuming the problem was given inside the context of complex numbers, but it wasn't. So do try to think a little bit about this problem 25 if you haven't already. I mean, I know you have because you've turned your homework, but I love this stuff in problem 27, but I'm not putting that on the test, so chill. Yeah. That's just that associative algebra matrix stuff that I love, you know. Anyway, I said I was going to stop there, so let me stop. Sorry, Kristen. Yeah. So I will see you Wednesday.